Okay, well, good afternoon to all the fine folks here at Supercomputing 17. I hope you've had a great conference so far. We're going to talk a little bit about the storage architecture that we've been using at Georgia Tech's PACE clusters. PACE is the Partnership for an Advanced Computing Environment. That means that, well, we have a large number of people that use the cluster. We have about 55,000 cores of cluster, and we have a wide variety of storage architectures that we use. So with that, number one thing that we have is really kind of three main tiers of storage that we run. One is Gpfs, Parallel File System. That is an IBM Spectrum scale. It is very high performance. It is very highly reliable. It's robust. It works very, very, very well. We have been using that for a number of years, and we've, knock on wood, we've never had a failure of it yet. And we have tried to stretch that in many interesting ways. And fortunately, the folks here at DDN have always been very good to us about helping us with any issues that we have had, but we've never really had any major issues. We also have NFS. It masquerades as ZFS. We run that typically under Linux. And we do have some highly available systems as well that run ZFS. But we tend to put certain types of architecture on that as well, and I'll just explain how we use all of these architectures in just a minute. We also have some object storage, reliability through replication. Objects you generally consider to be, well, you put them out there once and you probably read them multiple times, but you don't tend to change the objects quite as often. So you might ask the question, well, how do you do these first two, which are very much POSIX-centric kinds of file systems? The object storage is very much not POSIX-centric. So how does that fit into a POSIX world? Well, we'll talk a little bit about that too. So this is a fairly short talk, so I'm going to be kind of going through some of these slides a little bit quickly, so we try to stay on task. But for storage uses, we have things like software repository. Georgia Tech supports about 1.1 or 1.2 terabytes worth of storage of local software. Some of that is locally done, some of that is third-party software, but that has to be available on every single compute node that's out there. That's a little bit more than 1,500 of them. And in general, we typically make that read-only. We do that for a couple of reasons. One is we don't want people messing with the software. And number two is there's some caching that you can do with read-only that is only available if you're using it read-only. We also have home directories. And home directories, of course, are populated everywhere as well. If people want to run a job, typically they may run something out of their home directory. That's okay. We generally don't recommend that, but they can certainly do that. Project space is where all the rest of the storage is. Home directories we typically leave about 5 gigabytes. So not a lot of space there. Enough to try a couple of compiles, enough to run some tests and things, but not a lot to run a very large research application. The project space is where we typically would want to put that. So the project space has a very important part because that has to be the higher speed typically, again, available on all of the other cluster nodes that are there. We also have scratch storage, temporary space, of course, very typical of many other types of things. We also have some public addressable, accessible storage, things that are basically like a science DMZ, things that people need to be able to access outside of our cluster. So we're looking at ways to do that. And we have to have a little bit of archive storage as well. The archive storage is something that's going to last for some period of time, and generally it's going to be out there for some sort of a backup perhaps, or it may just simply be that you need to keep that for some long period of time. The availability is some of that storage, but not all, has to be available on every compute node and every utility node. So if you have a licensed server then it needs to check on what's going on, or you have a utility node which is there to help move data across different parts of the cluster, they only need to have certain parts of that. They don't need to have access to every single piece. We also have a set of restricted nodes, things that are restricted services. They may be ITAR or DFARS or things in that order. We have to be a little bit more careful about what kinds of storage is made available on that. So those are all different kinds of storage tiers that we have to supply. So how do we do that? Well, one of the ways to do that is to use Gpfs, Spectrum Scale. General Parallel File System is licensed by IBM. It is, as it says, sophisticated, very full-featured parallel file system. There are many, many different things that file system can do for us. That includes moving data, migrating data. That means you may have to grow a file system. You may have to shrink a file system. We have done things like pull disks out of the system while it was running. We have added disks to it while it was running. All of this is in full production. It never missed a beat. It's really one of the wonderful things that Spectrum Scale can do for you. It also supports very large and very small data. And what's really interesting about the research that we have at Georgia Tech is we do a little bit of everything. There's many different kinds of applications, many different kinds of research being done. And sometimes we'll have people who say, well, what I'd like to do is I'm going to come up with this brilliant new idea and I'm going to put lots of small files in a single directory. Maybe not what you wanted to do, but that was a great idea while you were in the shower or something like that. So we have those kinds of situations, and we also have people who say, well, I'm going to use a very, very large file. Something that maybe is 100 terabytes, maybe it's going to be bigger than that. Maybe I'm going to create a sparse file, it's going to be even larger, but we'll just have to wait and see what happens. But what we have to do is we have to scale all of this to all of the large cluster environment that we provide. So for NFS and ZFS, well, ZFS has been around a long time, NFS even longer, and it's a very well-known, very mature kind of a file service. It's been around. If you've used Unix systems for anywhere practically, you've probably used NFS somewhere. It's surprisingly capable even today, depending on the kind of a workload you're looking at. For example, we use that for the distribution of our software repository. It means that file system is mounted on 1,500 plus nodes, and it's available read-only on all of those nodes. And it's not a service problem, it's not a storage problem, it's not a performance problem, because of the way that NFS and ZFS does its caching. Typically, the system itself, the storage server, will do some caching. So the more someone asks for a particular file, the system will keep that cached in memory. But it also caches on the client side. So the more frequently a client system asks for that file, the client system will do some caching as well. And now you have some caching there. So let's say that you're running MATLAB or something like that. It may cache that on your local machine so that if you just run it again and again and again, it doesn't even have to ask the server for additional information. If you've been running it for a while and on some other machines, that means the server probably has it cached. And again, it doesn't have to actually go to the disk drives to actually get that file brought back up and into service. So it can really improve the performance rather dramatically depending on the workload. So the other thing that we do with that is home directories. It's like, well, why would you use something like ZFS for home directories? Wouldn't you want that on a nice big parallel file system? Well, not really. Because if you think about what do you do with a home directory, well, you store a few files there, you edit a bunch of files, you're going to be editing workloads and all that. It's all very interactive kinds of things, but you don't need a high performance for that. What you really need is just the accessibility and the stability for that, and NFS can do that. There are high availability products available. We have used that. We have some additional products from some other vendors that are out there. They provide us nice high availability NFS and ZFS. And that actually works out quite well for us. And we have had occasions where we've had a complete hardware failure on one of the head nodes for that ZFS file service. And the good thing is, nobody noticed. That's a really nice feature to have when you have that kind of a situation. Same can be said for Gpfs, by the way. And in fact, we had a situation where there was a failure in one of the two controllers that we had on the Gpfs system. And that happened late on a Friday night, and Monday morning we all come in and we're kind of looking around, looking at stats and error messages, and somebody says, "Hey, did we lose a controller?" And well, yeah, I guess we did. But the good thing is not one user noticed. Things just kind of continued on like they should, and that's really, really great. So the other thing you can do with NFS and ZFS, of course, there are things that's called protocol nodes are available from Spectrum Scale, so that you can actually have your Gpfs system provide you NFS service directly. That's really kind of nice. There are extensions to that. There is parallel NFS and all, but there's lots of different options you can look at for that. However, That provides a really nice medium tier of storage for a lot of different varieties of utilization. Then there's object storage. What in the heck do we want to do with object storage in high performance computing? Well, there's cloud storage. Well, a lot of that is object-based. You want to take an object-based file system and you want to take a look at what can it do for you. Well, you can use that for archive. You can say, well, I'd like to push this into this object space and I don't want to see it again for maybe a year and a half from now. I need to reference that file just to make sure that I have everything still where it's supposed to be. Or I had somebody request, what did you do for this particular data set on July 15th, 1971? You know, it's like, well, I'm sorry, object space didn't exist back then, you're out of luck. But if it happened a couple years ago, the good luck is that it's probably there, the object is still there. What's nice about a lot of the object space storage systems now is they will not only replicate your information across multiple locations, but they can also verify that on the fly. So periodically it does go through and double check to make sure that everything is correct in the object. If there's a discrepancy, it goes to find maybe multiple copies and it says, okay, which one of these is correct? It'll rebuild that object, create it, put it back out there. All of that happens in the background so that by the time you retrieve the object the next time, it's already still been corrected. That's great. Why objects in the first place? Well, a lot of people think about metadata for storage systems as, well, it's got ownership. You want to know who has read access to it. You might want to know what directory it's part of. That's all metadata. But there's a lot more metadata that you may want to keep. If you're into material science, for example, you may want to say, where did this material come from? What conditions created this material? What were the testing results of that material? All of those kinds of things are metadata that you can keep with the actual information in an object space kind of a thing. That makes it a little bit easier to do that way than it does with a standard POSIX file system. And again, automatic replication and retrieval. I can lose an entire server with a petabyte worth of object space storage, and I don't really feel bad because I know that it's been replicated somewhere else. I'll ask the same system for that same object and it says, oh, well, that one's not there right now, I'll go get it from one of the alternate spaces for you, all automatically. And a lot of it is you can also do the immutable objects, which is really handy if you're truly archiving information that you want to make sure is always there and always stable. So, one storage system for all? Not really. There's so many different ways that you might want to access data that there isn't any one system that works well for everything yet. And I think that's still the Desiderata out there. If anybody knows of a file system that works for absolutely every case out there, I want to know about it. But I haven't found one yet. There's always something somewhere that doesn't work quite right. And as it says, researchers still do very interesting things. We had one researcher recently that we were copying the data for them, and yes, they had put over 170 million files in a single directory. You can't plan for these things, I promise. And then we had another person who was in the same file system that said, hey, I've got this one sparse file and it's 23 petabytes and a 6 petabyte file system. Oh, wait a minute. So you try to copy that with the wrong way and such, and now you're trying to create a 23 petabyte file system somewhere else. That's just not a great idea. So what you really want to do with storage architecture is choose the architecture of what you're going to use based on the access need. If you're going to need fast information and it's going to need to be resilient, use a parallel file system. It could be Lustre, it could be Gpfs, it could be any of those kinds of things. If you're looking for a fairly medium tier type of a thing, like we do for our home directories or the distribution of software, you can do that with something like ZFS. It's okay. You don't have to always use one type of file system for absolutely everything that's out there. Everyone has its advantages, everyone has its particular good things that it does, and some things that it probably won't do well. So choose wisely. The other notion is more and more often, a lot of these centers, including those at Georgia Tech, are needing to look at distributed storage. It's becoming more and more necessary as we tend to outgrow data centers and we build another data center someplace else, and it's like, okay, now we need to put some compute side over that other machine room. How do we get that access to the data over here? Well, that's fine if it's only a mile or a couple of kilometers away. you might be able to bridge something like InfiniBand, but yeah, then you get past that. Yes, you can do InfiniBand over greater distances, but you pay a price for that. So there's lots of ways that you might want to look at that. Distributed storage is becoming more and more necessary. So that, and the fact that geographic dispersity is always a good idea, right? Diversity of what happens if the power is out in this data center. Do you have data over in the other data center that you can still utilize? That becomes important for certain types of workloads, not everything. Not all of our research data is considered to be absolutely critical to the nature of the existence of Georgia Tech. Much to the surprise and disappointment of some of the other researchers perhaps, but that is the case. So as far as the architecture goes, again, we look at project storage. We put that on our GPFS. We use our scratch storage that's also on another GPFS system. And we use DMZ storage. DMZ is another one of these things which a lot of people have been talking about for years. There are a number of people who have implemented it. It's implemented in slightly differing ways at times. But the reality is, what we're looking for is a very high-speed data transfer. So you can also call it a data transfer node. And so what we look for there is, how do I get a high-speed traverse of data from our data center to some other data center somewhere else in the world? And that's what Science DMZ is really all about for our needs. We still use GPFS for that, because what I'm looking for is, I've got a 40 gig or 100 gigabit Ethernet pipe coming in, and I've got to be able to collect the data that it comes in as quick as I can. Where am I going to put that? Well, probably not ZFS, probably not something like an object space. It's going to have to be something that's a little bit more like a parallel file system where it will actually accept that. The folks here at DDN can give you some really interesting ways of thinking about it. We don't have all of the solutions that they offer, but that's okay too. The other things, again, home directories, software repositories, protected storage, that all works out very well on things like ZFS. So we can continue to use that. We do use high availability for many things, not again all. Again, you kind of pick and choose depending on what your requirements really are for that data. If the power goes out and the entire computer room is down, do you really need access to that data and you need the high availability? Maybe not. There's probably other problems that you have to solve first. And then again, the object and archival storage, we tend to use Swift for that. So we've used SwiftStack, and we have a fairly large SwiftStack implementation that's been growing for some years. And that's fine too, but again, it has its particular uses. It's not for everyone and everything. Can I mount that object space on all of our clusters? I could. Do I do that? Typically not. The last thing I want to see somebody do is run an MPI job across a gateway into an object space file system. It can happen, just like you can do things like you can mount a tape and do your data access randomly to the tape. You just don't really want to do that. So how are you going to support all of this stuff? You have all these different architectures. What's the main thing that you've got to have? A good, clean, and fast network set. You want to use RDMA for data transfers as much as you can because it keeps the CPU loading down. It basically makes that available for other things, okay? I need this storage and memory over here to appear in the system that's over there. Make that happen, network. Great, RDMA works very well for that. The other thing is, you typically want to start with your backbone as a minimum of 40 gigabit these days, probably more like 50 gigabit Ethernets, 100 gigabit Ethernets. Newer technologies as they come out, you talk to the various other manufacturers here on the floor, they'll tell you that, oh yeah, 200 is coming out, 400 is coming out. It will be coming out fairly soon, so we'll have to do that too. The other thing that you need is support person or persons. And I'm looking at one of my coworkers here who's nodding his head saying yes. You've got to have a support person or a company that can really support you well behind the scenes, or both. And we tend to have a little bit of both, fortunately. That's a really good thing. And then the other part of replication versus archive versus backup. Replication is just really simple. It says I want to make another copy of this someplace else, and it's always going to be exactly the same. If I mess up my copy here, it's going to mess up the replication over there, and I really can't do much else to help that. With backup, that means that I probably have the ability to go back in time some amount and actually go back and say, I needed that file from 3 days ago when I know that I screwed it up. Now I can do that with a backup system. There's archive, which we talked about earlier, and that's saying I've got to put something out there and it's got to last for some years, perhaps, but it's going to have to be accessible in some fashion, not necessarily quickly, but I have to be able to get it back and have it be accurate. So the question becomes one of, where will you back up your 50 petabytes and growing of storage? Do you just duplicate all your storage? Well, that doesn't work for backup. Do you just archive that onto tape and put that on Iron Mountain someplace? You could do that, but every once in a while you have to refresh that information or you lose the bits. So there's lots of different considerations through there, and I'm not really going to have time to go through all of the details of that, but that gives you an idea of things to be thinking about. So with that, that's really kind of the end of the very brief talk. It was supposed to be 15 minutes. I went over just a little bit.
Just slightly, but that's okay.
So,
does anyone have any questions?
Yes. We have multipass for the disk. The question is, how do we do the high availability for ZFS? And the answer is yes. We use the multiple paths for disks, and we have different systems that are both connected to the same sets of physical drives, so that if we lose one of the systems, the other system can access everything that the first system could as well. Any other
question?
Sorry, I can't.
What is one DDN product that you'd like to have in our data centers today, and how would you choose that?
So what DDN product would I like to have? Oh, well, I think that's really easy. There's this really wonderful thing right here. It's called the IME. It would be really nice to have that in our system someplace, but that's something that we're looking towards and such. So yeah, there's the shameless plug for DDN. I am at the DDN booth after all. Yes? Why did I choose Gpfs over Lustre? There's a good reason for that. When we first started, Lustre was a very much Wild West kind of a thing. When it worked well, it worked really great, and when it failed, it was miserable. And over the time, that basically just meant that you had to have more and more people to be able to support Lustre than we had available. So with Gpfs, it was a little bit more of the case that I could rely on a corporation to help me out with that. And I could say, I need that support organization from that particular group, and they could do that, and that worked out for us. So that's where that came, and quite honestly, Gpfs has been more resilient over the years, and it just continues to get better and better with Spectrum Scale and their newer products. Yeah. So the question is, what would we use for an edge cloud kind of a thing? And I think it really depends a lot on number one, what is the cloud that you're trying to use, and what is the it's not just the technology, but it's also what is the budget, right? There's a consideration for how do you use the cloud storage. Sometimes that's really cost effective. Depends on how much you utilize that within the cloud, or how much you're going to be pulling in and out of the cloud and traversing that pathway. So in general, you can use S3, of course. Swift can also do some of those things. There are some products out there today that you can actually utilize to help migrate data from one type of file system into the cloud or out of the cloud. The user doesn't know that. The user says, I reference the file the same way that I always have, but now all of a sudden you can move that to wherever the cost-effective tier happens to be. So without getting into the actual product descriptions and such, typically what you want to do is probably either S3 or Swift. You may use Ceph. There's a lot of different object-based type things, but 90% of those are object-based. So the question is if you have some sort of an AI job, would you have the same sort of a recommendation? And I think I would, quite honestly. It really just depends on what you're going to try and do with that AI job and how it's utilizing that data. There are specialized file systems that might work better for that. But quite honestly, from what I have seen so far, things like the parallel file system is going to be the best, especially if you can have something like a caching device like the IME in front of that to help with the performance of it. But overall, it really depends. Are you looking for performance? Are you looking for reliability? Are you looking for the metadata? It just depends on how you're doing it.